let's get started. I would like to introduce Kaizen's own Tom Forsythe.
Thank you, William, and good morning, everyone. I'm Tom Forsythe from Kaizen, one of our army of experts on the cleaning industry and cleaning techniques and methods. And today what we're going to talk about is how can you be sure your parts are clean? Well, the proof is really in the testing. And today we're going to talk about testing methods for cleanliness. So here in our electronics world, why would anyone be worried about cleaning in the era of no clean? Seems a bit of an oxymoron. Well, fundamentally, the reason we're worried about it is because dendrites and ionic contamination can cause dendrites, which can cause shorts. And shorts are bad. Shorts cause failures, and failures are bad whether you're in the space business, whether you're sitting in an autonomous car, or whether you're just enjoying the conveniences that the modern electrical world has given us. All of those things mean failure is either life-threatening or undesirable. So therefore, having a method to understand where we stand on that is kind of a good idea. What I've got is a few methods that we're going to talk about, as well as an overview of how one might select a method. It's a little technique that I use, and I thought I'd share it with you today. It starts out with understanding the fundamental science behind any method that you might consider. What makes it tick? Why? What is it testing, and why is that important to you? And is that the right thing to be looking for? The next is the applicability to today's designs. Things that might have been effective last year or last century may not still be applicable today with today's highly dense assemblies that have stacked devices and line traces that are really tight, and other than connectors, precious little through hole, that sort of stuff. What does it cost to do that test? Is it a king's ransom? Is it a pittance? What's the challenge there? Next is how easy is it to do the test? If it's regardless of how effective it is, if it's a torture test to do, then that's really challenging. And the next dimension is, well, gee, how quickly do I get my results? Right, that's kind of a key factor that we need information, quality information rapidly. And by evaluating these different methods, we can probably make a good decision. So now let's move on to our methods. Well, there's sort of four basic methods that range vastly in sophistication, and we'll sort of talk about them one by one. First is visual. Well, it seems kind of obvious that both obvious and not obvious that, well, gee, of course we look at everything we make, and is that really a test method? Well, it is, and that's validated, of course, in the production line by SPI and for solder paste inspection and all the other inspection techniques that are there, the automated inspection. But it also comes down to not only operators, but inspectors that look at things. Sadly, it's among the least reliable, right? So if we look at the fundamental science, that reliability factor, it's really challenging. Yes, some contaminants are visible, many are not. Is it applicable and repeatable? Well, because it's human dependent, it's not really very repeatable. That's really kind of a challenge. The cost is just the time of a glance and looks, and that could be a lot or could be a little, so that could be positive. It's super easy to do, there's no problem there. And of course, you get immediate results. If you see a problem, you can act on that. So that's really pretty positive. So those are where visual falls in. Now let's look to a more scientific method, the Rose method. It's been around for a very long time. So the fundamental science is actually under further review, because while the science of the test is as it has always been since the 70s, how that science is applicable to what we're doing and finding our contaminants is very much changing, because the flux people are evolving no cleans are designed to be inherently safe, and their residues trace, which means they're harder to detect, not just from a quantitative perspective, but from their reactivity perspective. Their applicability, this is rapidly decreasing because Rose was designed in the era of wave solder, where contaminants were widely spread and copious, really handy. And now our contaminants are trapped under devices and are in very tight spaces. The cost of execution is quite low. It's an easy test to run. So those are really positive. And the timeliness is quite good. It hasn't really changed a lot now. The C3 folks have invented more of a site-specific method, which is really positive because that decreases the averaging risk. This averaging risk is, I say I've got a problem under one component, and I put a whole card in a Rose tester. Well, that one component may be problem may be detected, but then it's averaged over the whole scope of the board, which then mostly doesn't report a fault. The C3 folks have focused on that site-specific approach, which I think is quite important and wise. So that's kind of an important innovation there. Move on to ion chromatography. Ion chromatography, again, highly respected method. This is good science. You know, we're analyzing, we're separating species, we're understanding what's really going on. It's still applicable. It's used constantly in failure analysis when we're trying to figure out what went wrong. So it's highly regarded. Uh, Cost of execution can be high because it typically is done at outside labs. Likewise, the ease of execution, it's generally the actual IC part of this is generally done by skilled staff and equipment, which tends to decrease the ease of execution for someone local. Um, Once again, the typical IC method focuses on this whole board concept rather than the site-specific. The C3 guys target the site-specific sampling, which is really a positive. The timeliness of results, they're generally delayed simply because it goes to that outside lab. Now let's move on to surface insulation resistance. This is one where there's been some dynamics, right? The science is highly respected. In fact, it's required for new process validation, right? That seems to be the highest recognition of its effectiveness as well as its applicability. It is in fact completely applicable to today's designs. Because it is in fact testing underneath components, which is where most of the challenges reside today. It's not really in the land areas. It's not that broad-based risk. It's in that very localized area under QFNs and QFPs sometimes, that sort of thing. The cost of execution is one of the things that's changed. Historically, it was high. You had to send it out to a lab. So it was costly and it wasn't very easy to do. That's changed. Now there's integrated systems that are available that bring the chamber that's needed. These are testings that's done at high temperature and heat and humidity that allows for the accelerated life part of this. The validation tests, of course, here run for 7 days to really get that full accelerated life dimension. But here on when we're looking for more rapid results, we can get real-time results during those 7 days, as well as draw some very strong inferences from the early data in the first couple of hours. And I think what's important to recognize with this method is rather than hunting for contaminants, what this method does is it actually evaluates the electrical effectiveness of the circuit. Are we moving the current and voltage around? Are we not being impeded by any contaminants or other problems that might bridge a circuit or cause a circuit to fail? And that's a real difference. One of the other challenges is that it does use a test coupon rather than the original part. Well, in our era of twins, you know, where there's a great deal of writing and discussion about the notion of the digital twin to try to model and mimic everything we do without having to run the risk on our factory floor. Well, these surface insulation resistance techniques also use a electrical twin where you're using a test coupon, could be a break-off coupon, that really is very representative of what you're doing, but doesn't put your production at risk. You're not actually doing testing on product that you want to shift to a customer, particularly if you're a no clean house. Even the water and IPA solutions in both the IC and the ROSE testers can adversely affect some of the no clean encapsulants. Typically, ROSE tested boards would be shipped to customers, but IC tested boards generally are not. So you know, that's a real challenge there and an advantage of this sort of method, this electrical twin idea. But it also, much like the C3 does, it brings things back around to this focused risk. Where are the site-specific, hole-to-hole, pin-to-pin risks underneath components and very densely packed components? And how can we identify and measure those? So that's a key advantage of this SIR technique. And this new applicability opportunity is a real plus. So when we come back to our conclusions, you know, there are a variety of methods backing up and looking at what are we measuring, understanding the fundamental science. Is the science doing what we're worried about? If we feel like we have a fever at home, we take our temperature. We don't measure our height. So are we doing the right thing? Is the test method well suited to today's designs? The the disappearance, or not disappearance, but the great decline of wave soldering across the board really limits the applicability of ROSE and IC in that whole board testing method, whereas the site-specific techniques are really effective. Are they cost effective? Are they easy to do? And do they get your results rapidly? So I'd like to thank you for attending today, and that'll wrap up our talk. And now, William, I'd give it back to you and let me know if there are any questions.
All right, thanks, Tom. If you would like to discuss this topic further, please contact your local Kaizen representative or send an email to tech@kaizen.com. And we will have one of our cleaning experts schedule a follow-up with you as soon as possible. Again, thank you all for joining us today, and we hope to see you again soon. Stay safe, stay healthy, and have a great day.